So this is the second class of the magnetism. In our last class, we talked about how does a free moving magnet aligns itself with a pre-existing magnetic field. It always aligns itself so that the North Pole is close to the South Pole and the South Pole is close to the North Pole, which brings us to the idea for how the Earth's magnetic field line works. So this is how any bar magnet, if it's placed close to the Earth's surface, this figure is not drawn to scale obviously, aligns itself so that it always shows the North Pole to the geographic north and the South Pole to the geographic south, which brings us to believe that the Earth's magnetic field must enter through these bar magnets, hanging bar magnets, to the South Pole side, and they should come out in the North Pole side. And this is actually true for all the individual positions as well. So this basically means that Earth's magnetic field lines go around like that. So from the South Pole, they move towards the North Pole. So Earth's magnetic field lines happens to come out from the South Pole at a certain latitude, from which we can actually start to see the northern lights or the aurora, and that actually happens due to the ionizing radiation that enters into the Earth's atmosphere, that ionizes the Earth's atmosphere, and that gives out a certain type of radiation which shows up as some sort of light, pretty beautiful to see. But Earth's magnetic field lines happen to work in this fashion. So this is how the orientation of Earth's magnetic field lines are. They come out of the South Pole and geographic South Pole and enter into the geographic North Pole. So this is the actual orientation of Earth's magnetic field, which brings us to believe that Earth behaves as if it has a magnet embedded within itself in such a way that the magnetic field lines are coming out from the from the geographic South Pole, and they are all entering into the geographic North Pole. So if I assume that there is a bar magnet that is hidden inside the Earth, and if I represent this bar magnet to have a shape somewhat like this, for this bar magnet, the field lines are coming out of the geographic North Pole, and they are entering into the geographic North Pole, and they're coming out of the geographic South Pole, which essentially means that for the Earth, the geographic North actually holds the magnetic South, and the geographic South actually holds the magnetic North. This is the idea of Earth's magnetic field. The reason this is upside down or is sort of reverted compared to the geographic and the magnetic side is because the people, the human being, we have been using the magnets to find out the position of the North Pole for a really long time, and we have always defined the north aiming side as the North Pole side of the bar magnet and south aiming side as the South Pole aiming bar magnet. So that's how the orientation of these used bar magnets or hanging stones, which are called lodestones, were used. The whole idea of magnetic field lines, then the Earth should have its own magnetic field lines, and that should get down to the point of Earth having its own magnetic field around the Earth. That's why the orientation of the bar magnet hangs in this orientation. These ideas were generated far more later. So the scientists decided that we are not going to shift or they change the name of this pole. So we're not going to say that this end of the magnets is a South Pole, this is the North Pole. We're not going to do that because that has been in use for a pretty long time. Rather, we'd simply say that Earth's magnetic field and Earth's magnetic poles and geographic poles are just reversed. So if Earth is considered as a pretty large magnet, the South Pole of Earth's magnetic field happens to exist on the geographic north, and North magnetic pole of Earth's magnetic field happens to exist on the geographic South Pole. This is the basic idea that I wanted to show you in the last class, and that's the thing about it. That's point number one. The other thing that we need to consider as for magnetic field lines is that how can we draw the magnetic field line of a bar magnet by an experiment. There is a very nice piece of experiment that is in a certain page number of your federal book. I actually forgot the page number, but the figure looks somewhat like this. Let me just show you this figure. Yes, this is the actual process. So I'm gonna just show this video to you. It's a 2-minute video, pretty small video. So let's have a look at it, and it will make good sense to you other than me blabbering through the whole process.
It's probably safe to say that you have a
this one.
very good idea of how the magnetic field of a bar magnet looks like. But do you know the 4 important properties of magnetic field lines? To find out, let's begin by plotting some magnetic field lines. We need a pen, plotting compass, and a magnet. A magnet
A plotting compass is simply a small magnet that is placed within a magnetic compass that looks something like this. This red marked side is usually the north pole side, and the empty part is always usually the south pole side. So this whole pin shaped or this rhombus shaped magnet, which we call a needle magnet, is actually placed on a very small fine pivot, and this black part that you see is actually a hemispherical cap. Underneath that cap there is a single point support, and this magnet is perfectly balanced onto this support. As a result, it can pivot around or rotate around that support point pretty easily. This thing is made really balanced, and the magnetization is also done really precisely, so that this end is always the north pole, and the colored end is always the north pole, and non-colored end is always what's at the south pole. So this is a bar magnet. Usually the red side is the north pole side. We're going to see about that right away. So have a look.
doesn't tell me which is the north pole and which is the south, but we'll find out soon. Place your magnet in the middle of the page and trace around it. Place the plotting compass near the magnet. Mark the direction that the compass needle points by drawing a dot. After the first plot, move the compass so that the back of the needle lines up with the dot. Repeat this until you reach the end of the magnet. Join the points together to show a field line. I'll also draw an arrow here to show the direction that the needle is pointing in. I'll do all of the above again with another starting point. Looking at the field that we've plotted, we can figure out the 4 main properties of magnetic field lines. Number 1. Magnetic field lines never cross each other. They never overlap. Number 2. They always point from the north pole of the magnet to its south pole. North into south, so that must mean that this is north and this is south. Number 3. They are continuous. The only reason these lines have been cropped out here is because I've simply run out of space.
Continuous in this case mean that these lines actually does not finish at the end of the magnet. What it actually means that this magnetic field line which is coming out of the north pole is not starting to create itself from right of the edge. This magnetic field line was created from inside the magnet, and that moved through the magnet and came out of the north pole, went on the outside of the magnet, it traveled from north to south outside the magnet, and then it entered through the south pole, and eventually it actually traveled through the magnet continuously and eventually went through this process again. So these magnetic field lines which actually seen to start from the north end and eventually get finished at the south end, they're not actually right over there finished. They are actually continuous lines which are also move through the magnet itself, but because we cannot simply place our needle compass exactly inside the bar magnet, that's why that part is not drawn. But this is more easily visible or more vividly visible for the case of a solenoid, which I'm going to see after a while.
Number 4. Where the lines are closer together, the magnetic force is the strongest, and that's at the poles of the magnets.
Okay, so that's a pretty nice video. বুঝা গেছে কি প্লটিং কম্পাস কিভাবে আঁকতে হয়?
Yes, sir.
আমি স্টেপস গুলো একবার একটু জাস্ট শর্টকাটে বলতেছি। স্টেপস গুলোর মেইন পার্ট গুলো হচ্ছে, first we have to place the bar magnet onto the white piece of paper, draw the outline. The reason we need to draw the outline is that in our experiment process, at any point, because of some shake of some error, the bar magnet could move from its original position, and we need that outline drawn so that we can replace the bar magnet in the same position to continue with our experiment. So we need draw the outline first. Then we're going to place the plotting compass close to one of the end of the bar magnet and give 2 dots. Actually, this person actually started from the further part. Actually, we prefer to give 1 point right over here as well. That's how the syllabus says it. So we give 2 points on the two ends of a needle compass. Then we take the needle compass away from the magnet and place it in front of the farther point such that rear end of the needle compass perfectly aligns with it. তার মানে হচ্ছে আমরা আমাদের একটা পয়েন্ট আঁকার পরে এরপরে আমাদের নীল কম্পাসটা আমাদের প্লেস করতে হবে যাতে করে নীল কম্পাসের এন্ডটা ওই পয়েন্টটাকে পারফেক্টলি এন্ড করে, and then we're going to put another dot in front of the front part of the needle compass, and we're going to repeat that process till we reach to the other end of the bar magnet. So we can draw this. I mean, drawing this once gives you one field line. This person went to draw actually 1, 2, 3, 4, 5, 6, 7, 8 field lines when that part of the video was fast forwarded because it was not very much it's repetitive and pretty much the same thing done. So we do that, and then that's how you get the dot positions. That's not drawing the line. Then you have to also mention, if the question asks you that how this experiment can be done, that we join those dot marks with a freehand line, and those lines gives us the magnetic field lines. This is the basic procedure. There is a small precaution for this experiment which is really important. The precaution is that whenever we're going to give the dots on the two ends of the needle compass, this one, we will tap the table a little bit. Tap means give it a bit of a knock, slight knock. The reason we need to tap the table because these needle compasses are actually designed to have very small friction at the support point, but there can be some friction, and if for some needle compasses which are not manufactured well or they have been used for a really long time, the friction might get increased. So whenever we do a little bit of tap, that tap actually helps the needle compass to overcome that possible friction that exists at the pivot point and make itself perfectly aligned for our requirement. So that's why we need to give a little bit of tap before we give our dots for each individual position. This is not actually shaking the whole table. Just give a little bit of tap, so there's a little bit of vibration on the table surface. Everything stays in the position, but the whole setup experiences a little bit of shake, so that if there is a bit of a friction, that friction is basically overcome. This idea of friction overcoming by a little bit of tap is very much similar to whenever we try to fill up jars with multiple stuffs like muri or chal or rice or some other things. So you put some stuffs in there and it's almost filled up to the top. Then if you give it a bit of a shake, you can see that more space is created. What happens within that shake, the in between friction can be overcome, and the particles in between gap are more filled up by solid particles because they can now move around in a zigzag pattern and they can compact more. This is also the reason why compacting is needed for any type of new road construction. If in any city corporation is making some new roads, the road has to be compacted first, so that all the layers of road materials, bricks and then cement, and then if you are using tar and stones mixture for the carpeting, they have to definitely compact the ground first, so that after the whole construction, the whole thing doesn't actually sit down or it doesn't fall below the level. So these are some pretty important parts. There is one other experiment over here. This is for using very small iron dust or iron particles, which can be also used to show the magnetic field orientation for a pretty interesting view. I'm going to play this video as well. I'm going to share the links of both of these videos in my description, so that I might be able to avoid the copyright issues. But I want all of you to see this video here. Have a look at this one, then we're going to give a small break for Maghrib prayer, and then we're going to come back again.
अस्सलाम वालेकुम। लास्ट वीडियो में हमने ये सीखा था कि अगर हमारे पास एक सिंगल आइसोलेटेड मैग्नेट
Okay, this is in Hindi, but do all of you understand Hindi?
Yes, sir.
Okay, that's one person. How about the other four?
Yes, sir.
Yes, sir. Yes, sir.
ना बुझले আমি আবার বুঝাই দিব, no worries.
हो उसकी मैग्नेटिक फील्ड किस तरह की होती है और हमने उसका कैसे पैटर्न ड्रा करना है। तो आज की जो वीडियो है इसमें हमने ये सीखना है कि अगर आपके पास दो मैग्नेट्स हों और वो दोनों एक दूसरे के करीब हों, तो फिर इस केस में जो दोनों मैग्नेट की कंबाइन जो मैग्नेटिक फील्ड का पैटर्न होगा वो किस तरह का बनेगा, वो हमने देखना है। तो सबसे पहले देखिए, हमने मैग्नेट ऐसे अरेंज किए हुए हैं कि दोनों मैग्नेट के नॉर्थ पोल जो है वो आमने सामने है। तो इस केस में देखते हैं कि मैग्नेटिक फील्ड का पैटर्न किस तरह का बनता है, और बिल्कुल इसी तरह जिस तरह हमने लास्ट वीडियो में मैग्नेटिक फील्ड का पैटर्न बनाया था, उसी तरह हम मैग्नेटिक कंपास के जरिए से इन दोनों की कंबाइंड मैग्नेटिक फील्ड का पैटर्न भी बनाएंगे। तो ये देखें, अगर मैं कंपास को इस जगह पे रखूं तो इस जगह पे देखें मैग्नेटिक फील्ड की जो डायरेक्शन है वो किस तरफ है, जिस तरफ नीडल पॉइंट कर रही है। और इसी तरह अगर आप यहाँ पे देखें तो नीडल जो है वो बिल्कुल यूँ स्ट्रेट पॉइंट कर रही है। और इसी तरह यहाँ पे,
Beautiful demonstration.
और इसी तरह यहाँ पे देखें।
This teacher is showing us, he is showing us all the individual position of the magnetic field lines for individual points. Basically, drawing a combined magnetic field lines for different positions.
अच्छा ये देखें, ये हमने इसकी मैग्नेटिक फील्ड का पैटर्न ड्रा कर लिया। अब हम इन सारे एरोज को आपस में ज्वाइन कर देंगे तो आपको एक पैटर्न मिल जाएगा इन दोनों फील्ड की वजह से। तो ये अगर हमारे पास दो बार मैग्नेट हों जिसके नॉर्थ पोल आमने सामने हो तो उनका जो मैग्नेटिक फील्ड का पैटर्न है वो इस तरह का। तो अब इसी को हम अब आयरन से देख लेते हैं। मैं आयरन के छोटे छोटे पीस इन दोनों मैग्नेट्स की विसिनिटी में फेंकूंगा तो आप ये देखेंगे कि वो आयरन जो छोटे छोटे पीस होंगे वो भी इसी डायरेक्शन में अपने आप को अलाइन करेंगे। तो अब ये देखें, हम इनके ऊपर जो है वो छोटे छोटे आयरन के पीस फेंकते हैं तो वो बिल्कुल आयरन के जो छोटे छोटे पीस होंगे वो अपने आप को इन्हीं मैग्नेटिक फील्ड की डायरेक्शन में अलाइन कर लेंगे।
They're extremely small pieces, or like dust iron, or like particle iron, or you can say iron fillings, so something that we can get whenever we machine a piece of solid iron with file. Do you guys know what is a file? Bangla red bole. It's a thing that you can rub on stuffs and actually take away. It's something similar to emery paper or sheesh kagoj.
अच्छा ये देखिए, मैं अब आयरन के छोटे छोटे पीस इसकी विसिनिटी में फेंकूंगा तो अब इन्हें देखना है कि किस तरह ये आयरन के छोटे छोटे पीस मैग्नेटिक फील्ड की डायरेक्शन में अलाइन हो जाते हैं। तो ये देखें, जिस तरह का हमने एक्सपेक्ट किया था बिल्कुल इसी तरह का ही पैटर्न बन रहा है। यहाँ से मैग्नेटिक फील्ड जो है वो बाहर की तरफ डाइवर्ज हो रही हैं और इधर जो है वो क्लोज लूप बना रही हैं। ये वाली जो मैग्नेटिक फील्ड लाइंस हैं ये भी क्लोज लूप ही बना रही हैं। तो मैंने आपको पिछली वीडियो में बताया था कि जितनी भी मैग्नेटिक फील्ड लाइंस होंगी वो क्लोज लूप बनाएंगी, लेकिन आप यहाँ से देखें कि ये एक दूसरे से ये जो दोनों मैग्नेट हैं ये एक दूसरे की मैग्नेटिक फील्ड को बेंड कर रहे हैं और ये दोनों मैग्नेट इस टाइम रिपेलिंग कंडीशन में। अब हमने जो है वो पैटर्न बनाना है कि जब मैग्नेट का एक नॉर्थ पोल और एक साउथ पोल दोनों आमने सामने हैं तो अब हमने इस तरह का पैटर्न बनाना है कि इनकी मैग्नेटिक फील्ड का किस तरह का पैटर्न। तो देखिए उसी तरह हम करेंगे, मैग्नेटिक कंपास को रख कर
Irfan, I'll tell you answer. Just give me a moment. ভিডিওটা শেষ হোক বলতেছে।
हम दो मैग्नेट रखें तो इस तरह का मैग्नेटिक फील्ड का पैटर्न बनता है और आप ये देख लें कि दरमियान में जो मैग्नेटिक फील्ड है वो मैग्नेटिक फील्ड लाइंस की जो डायरेक्शन है वो नॉर्थ से साउथ पोल की तरफ है। तो अब हम इसको उसी तरह वेरीफाई करेंगे आयरन फिलिंग इसकी विसिनिटी में गिरा के, तो जो आयरन फिलिंग होगी वो अपने आप को मैग्नेटिक फील्ड की डायरेक्शन में अलाइन कर लेंगे। तो बिल्कुल देखिए इसी तरह का पैटर्न बनेगा जिस तरह का हमने ये बनाया हुआ है। ये देख लें जिस तरह का हमने पैटर्न एक्सपेक्ट किया था बिल्कुल उसी तरह बन रहा है। यहाँ पे देखें मैग्नेटिक फील्ड लाइंस की जो पैटर्न है वो इस तरह का है और दरमियान में मैग्नेटिक फील्ड लाइन का पैटर्न इस तरह का।
Beautiful demonstration. Nice, really nice. So Asif asked me one question. I'll answer the question, then we will take a small break. Asif asked me the question. So the magnetic material is not attracted to the magnet, but it is attracted to the magnetic field. Here's the thing. The magnetic particles, which are the iron filings or iron particles, small pieces of iron, they are attracted to the magnet. How are they attracted to the magnet? Not the why. How are they attracted to the magnet? We use the idea of magnetic field lines to explain that. Do you get my point?
So if the iron fillings were attracted to the magnet, why didn't they all like cover up the magnet?
That's a pretty interesting reason, because if I just show you over here, whenever the teacher was actually dropping these iron fillings, let's say over here, iron fillings experience gravitational force because they have weight, and they're also being attracted by the magnet as well. So the magnet over here is actually making a three-dimensional spaced magnetic field orientation. So this is not only exclusive for the plane of paper. This is also equally applicable over the magnets and through the bottom of the table. I mean, it's a three-dimensional, like a three-dimensional bowl kind of shape or a balloon kind of shape. But the force of Earth's gravitational pull is quite strong on the iron fillings. So whenever the teacher is dropping them from a certain height, they are falling down because of Earth's gravitational pull pretty strongly. At the same time, they're having a little bit of deflection because of the magnetic field's attraction, or because of the effect of the magnetic attraction of the two magnetic poles. And that's how they actually fell down. And whenever they only fell down, they didn't have much of a good orientation, for example, before the knocking started. So here we can see the pattern is actually visible, but not that well. But when the teacher starts to tap on the bench, you can see that. So here all the iron fillings are in individual positions, and you can see some small alignments for lines which are somewhat representing a line. The lines are actually not very visible because all of these things are getting attracted by the magnet. Very true, but the friction that exists between these particles with the paper because of the Earth's gravitational pull downwards is not allowing them to travel to the magnets. So whenever the teacher is going to tap on the table a little bit, they're going to overcome those frictions for each individual tap slightly, which means the contact force is going to be a bit less because of the vibration. And as they will land back onto the paper, they are going to realign themselves with the effect of the magnetic field lines. So they are attracted by the magnet, and how does that attraction work? We use the concept of magnetic field lines to explain that. Does it answer your question?
Yes, sir.
Clearly বুঝা গেছে?
Yes, sir.
স্যার আমার একটা কোশ্চেন ছিল।
Sure, জান বলো।
ম্যাগনেটিক ফিল্ড লাইন তো এগুলো 3 ডাইমেনশনাল তাই না?
Yes.
এফেক্টটা সো আমি যদি হচ্ছে কিছু আয়রন ফিলিং মাটিতে দিয়ে রাখি, তার কয়েক ইঞ্চ উপর যদি আমি একটা ম্যাগনেট দিই তাহলে এফেক্টটা কেমন হবে?
We're going to see the exact same effect. Exact same effect means, what I'm trying to say is that, let me show you. Hold up. Let me see if we can actually find a three-dimensional magnetic field orientation diagram that is manageable. Physical class হইলে আমি খুব easily বুঝাতে পারতাম, but let's we'll take a break for this, and I'm gonna do my research, and for those who want to say your prayer, please take a break. This is a representation for how the magnetic field lines of a bar magnet or a cylindrical magnet exist around itself. So this is how the animation looks like. If we play it, this is how the magnetic field lines come out of the object and then comes back. So I'm gonna change the size of the magnet. Zooming actually takes care of the problem. So the magnetic field lines actually come out of the object and then they move into the bar in the south pole. So here the top side is the north pole side, and magnetic field lines are coming out like this. This is something like a pumpkin shape. But what I need all of you to understand is that magnetic field lines are imaginary lines represent the direction and existence of magnetic field within a certain region. Close field lines represents stronger field, further apart field line represents weaker field. It doesn't necessarily mean that locations where the field lines are drawn, exactly at those points we have the magnetic field. Magnetic field is available everywhere. We are using this imaginary number of field lines to represent how the field lines have their direction and their orientation. So you shouldn't believe that places where the field lines are not drawn, those locations are void of magnetic field. No, everywhere around this magnet there is a magnetic field distribution. These field lines are representing the location and orientation of the magnetic field of these exact locations, which essentially means if we drew bigger circles, for example, let's say if we drew bigger circles, so magnetic field line would still be on the inside, magnetic field lines would still be on the outside. So we can have magnetic field lines all around the whole thing. Well, there is some pretty nice videos available in the YouTube, which I'm going to show you. So what I did search, hold up. This is where I actually did the search, I believe. Yes, I wrote 3D magnetic field, and I had a lot of different things, and I checked multiple of things of those. So first, have a look at this one. This is a setup that this demonstration is using, where this scientist or demonstration person, scientist, physics teacher, whatever, he has set up a really big number of needle magnets with a small pivot or rivet point where all of these needle magnets can actually move freely. And whenever he's going to place this bar magnet inside this hole, they're going to all align up pretty nicely like that. So let's just have a look at this video. It's a very small video, but the actual rivet part is actually pretty small. So we're going to see how the bar magnet actually behaves for a
270 little compasses attached to the field demonstrator. Now, if we look at a bar magnet, this is a cylindrical bar magnet. You don't see too much. It's got a north and a south pole, but you don't see the magnetic field at all. But if you bring it up near the magnetic field demonstrator, you'll see that the little compass needles align themselves with the magnetic field lines. So let's see what the magnetic field lines look like around the whole bar magnet. Now the field demonstrator has a removable panel. You insert the bar magnet, slide the panel back in again, and there we have it. The invisible is revealed. So each of the little compass needles are aligning themselves with the magnetic field that surrounds the bar magnet. Now the convention scientists use to draw magnetic fields is that the magnetic field lines come out of a north pole and loop around into a south pole.
Does it make sense somehow?
Yes, it does.
Another pretty nice thing which was shown, I think. No, not in this one. This was not the one. This one? No, not this one either. Before this one. This is a really simple video, and this device can be also made in your house as well. So let's have a look at this one. We have a it says cow magnet. I don't know what that is. I think it's just a cylindrical magnet. There is a test that is attached to the lid of a bar. Here we have a clear jar, glass jar, through which we can see. We have some mineral oil, which is going to work as our suspension medium for the iron fittings. And here we have some powdered iron. So this thing is going to be made in 3 minutes 25 seconds of video. Have a look at this one. It's a pretty interesting one, and you're going to see the effect real beautiful. Have a look. three-dimensional field looks like for one pole. The other pole also has it, but the other pole cannot work because the tube is not that long. As you now move the magnet, see what happens. The iron fillings are also gonna move after the test. For me, it's very difficult. I don't know how you guys feel, but I feel good. Really good. So does it make some sense?
Yes, sir. স্যার আরেকটা কোশ্চেন ছিল এই
আচ্ছা কিন্তু
এই যে হ্যাঁ স্যার
আমি তোমার কোশ্চেনের আনসার দিই না। তুমি যে কোশ্চেনটা করছো সেই কোশ্চেনটা ছিল এরকম যে what if these magnets were placed above the level of paper? That's the question that you asked, right? How the field
Yes,
lines are going to look like if we place it exactly above the paper. So this is something that I'm going to draw for you to make sense. Try to understand for three-dimensional spacing. আমি just
স্যার
হ্যাঁ বলো।
এটার আগে আরেকটা কোশ্চেন ছিল এই যে এক্সপেরিমেন্টটা দেখালেন
Yes, yes,
এইখানে যে আপনি বলতে পারবো
বলো I'm hearing.
এখান থেকে এখানে যে আমি টিউবটার ভিতরে ম্যাগনেট ঢুকালাম ম্যাগনেটটা সরা দেওয়ার পর ম্যাগনেটিক ফিল্ডের এফেক্টটা লাইক কিছুক্ষণ থাকে নাকি সাথে সাথে স্টপ হয়ে যায়?
These are iron fillings which are magnetic material, but they are not permanent magnet. I actually didn't teach you this yet. Magnetic materials can be of two types, which are called soft magnetic materials and hard magnetic materials. Soft magnetic materials are those which can become temporary magnet under the effect of another magnet, and if that another magnet is taken away, they lose their magnetic behavior. So in the presence of a magnet, they have an induced magnetism. That's those type of things what we call soft magnetic material. And there can be hard magnetic material which has a tendency to store magnetic behavior within themselves once they are magnetized. They are difficult to magnetize, but if we can somehow magnetize them, there are processes by which we can achieve this. They are going to retain magnetism within themselves. So this bar magnet, cylindrical magnet that the person used, this bar is actually made from hard magnetic material which can retain or store or preserve magnetic properties within itself. And these iron fillings, they are soft magnetic materials, which means as long as this bar magnet is near to them, they're gonna act like a magnet. That's why they are getting attracted and such. But the moment this magnet is pulled out, they're gonna lose their magnetic behavior altogether.
জি স্যার
It's very much similar to something that you can think about like a regular class. I mean, the teacher is not there, kids are all jumpy and stuff, and teacher comes in. If the kids are scared of the teacher, in most cases, which was pretty nice, they are all pretty straight and they are not making a holler in the class. So something like that. So in the presence of a bar magnet or the soft magnetic materials behave like a magnet, and then when the magnetic field vanishes, they don't keep on behaving like that. That's why when the magnet was falling out, they all fell off right off the edge of the outside of the test tube because they were not working as magnets. So they themselves don't have a magnetic attraction force within themselves. They're just iron pieces, pretty much like any type of dust particle, like powdered milk or flour or powdered sugar, something like that. They're just like that kind of particle. But whenever you bring them close to a magnet, they start to behave like magnets, very small magnets, which actually line one upon another, which gives you rise to this kind of small spiky things because they all line up that way.
ওকে স্যার বুঝেছি
Beautiful. question that you asked me that what is going to happen if we have a setup like this. Let's say I'm going to draw this for you. It's a pretty nice question. Let's say we have a piece of paper. I'm trying to draw it in a bit of 3D, and we have, let's say, a piece of acrylic. I'm just using acrylic because I would appreciate a transparent medium. So piece of acrylic. Drawing a piece of acrylic is proving to be more difficult than it should. So let's say this is a three-dimensional object, or maybe a piece of glass, whatever, rectangular glass block. So let's say what we're gonna do, we're gonna put a bar magnet on top of this acrylic piece, which means this bar magnet is gonna be now at a much higher level than the level of the paper. So let's say this is our north pole side, and let's say this is our south pole side. And then we're going to sprinkle some iron fillings onto the piece of paper, except for on the bar magnet. So we're gonna spread iron fillings around the whole thing, and then we're going to tap onto the bench multiple times. We're going to still come across a figure that is very much similar to this one, but we are going to see a lower section of the pumpkin shape. I mean, try to think about it. I cannot actually show you how a pumpkin actually looks like. Try to think about it. Let's say you have a pumpkin which somewhat resembles the shape of magnetic field lines. If you cut exactly through the middle, you're going to get a spread around shape pretty much like this. But if you don't cut exactly through the middle, if you cut a little bit on the side so that one piece becomes a bit bigger, the other piece becomes a bit smaller, wouldn't you still get that same expanding shape? Not the exact one, but wouldn't you get a similar shape? You getting my point? No.
Yes, sir.
No, you're not getting my point. What I'm trying to mean, exactly at this level, the magnetic field lines are going to be like this. Some field lines are going to be coming out like that. Some field lines are going to be going in. Some field lines are going to go down. They're going to be along the page, around this level. Some fields are going to go up. Some fields are going to be like this. So I'm actually drawing for South Pole, so these field lines are all going to be inside. So this is how the field lines are going to look like. So if you have a three-dimensional field, let me just come up with this visualization. So let's say we have this three-dimensional field. Okay, I've been showing you what we're going to see. Not to make this rotate. I wish I could make it rotate. How can I make this rotate? I cannot make this rotate. So what I'm trying to mean is that currently we are seeing, if we cut right through this line, try to understand where I'm moving my mouse. Can you see the movement of my mouse? Right across this line. If we cut it across that, let's say we're going to do this for 12 and redo. So what we are seeing right now is what is going to be seen if we have a perfect middle line view. So shown the magnetic space exists on a piece of paper. What should you see if we had this piece of paper a bit below the magnet? Have to think about it. This is the orientation of the magnet. I'm going to give you the link as well so that you can see this thing for yourself too. All right. So if we place the piece of paper somewhere along this line, so let's say I cannot draw this, so maybe I will do print screen. Print screen. So the current view of the pumpkin shape is seen whenever the magnet and the paper is all at the same level. The problem that you asked is applicable when we have placed the magnet a little bit above this thing. So let's say the plane of paper is somewhere over here. So you are going to see a section of this line, a section of this line, a section of this line, section of this line, section of this line, section of this line as well, which means you're not going to see this much part, but you're going to see that expanding behavior as well. Still, you're going to see that. So if you try to visualize this thing for the part, you are going to see cutaway point, let's say somewhere along this line, along somewhere a line over here. Is there a way to draw on the screen? No, there is not. So somewhere along this line, if we have a cutaway point over here, we're still going to be seeing this part and this part and this part. We're going to see the lateral view of all of those segments. So which means we're still going to see an expanding part, but that's not going to be as vivid as the view that we might have got if we did draw it through the exact middle. But we're still going to see that expanding behavior. বুঝছো কি বলছে?
জি স্যার।
Okay. So that's what I wanted to say. And there is another thing that I'd like to show you. I'd like to clear the annotations. How do I do that? How do I remove this drawing? The other thing that I wanted to show you from this thing that I found very interesting was a similar thing like this one. Yeah, this is actually an experimental setup, but they are going to put this North Pole South Pole bar, cylindrical magnet in the exact halfway point. This is an acrylic hollow cube filled up with iron fillings. It's pretty much the same stuff, but a more beautiful one. So he's now jumbling all the particles. So this is all the particles are still particles. They are under the effect of gravity, but the moment the magnet is placed inside, they start to behave beautifully. I think that's enough for the magnetic field. Do you have any question yet?
না স্যার বুঝেছি।
The next thing that I will discuss is about soft magnetic materials and hard magnetic materials. I have told you a little bit earlier. Soft magnetic materials are those which have magnetic properties within themselves, but they cannot store that magnetic property without the presence of another magnet. And hard magnetic materials are those they can retain, preserve, store the magnetic property within themselves, which means they can be converted into permanent magnets. So soft magnetic materials can be magnetized and demagnetized pretty easily. It's very simple. For example, a simple piece of iron nail. If you have a simple piece of iron nail, it doesn't have any magnetic behavior of its own. But the moment we bring a bar magnet, let's say a North Pole South Pole magnet close to it, it's going to get attracted. And here's the catch. When does a magnet attracts another object? Whenever that another object also behave as a magnet. What kind of magnet? Like opposite pole. Try to understand. Whenever there is attraction between two supposedly magnetic thing, attraction necessarily means opposite poles are close. So opposite poles closure is going to give you attraction, which means whenever this bar magnet is brought close to iron nail, by means of induction, and now you might wonder what kind of induction is happening here. Let me show you. This bar magnet produces a magnetic field around itself, something like of this sort, right? Some of these magnetic field lines is going to enter through this iron nail from the side, and they're going to pass through the top tip and usually come out over here. So try to visualize what is happening for this bar magnet. From the side and also from the behind, magnetic field lines are entering, and pretty much through the tip the magnetic field lines are coming out. So for this object, the location where the magnetic field lines are coming out must be the North Pole side. The locations where the magnetic field lines are entering in must be the South Pole side. So now you have a South Pole from the bar magnet and a North Pole, induced North Pole, induced because this was created because of the effect of the bar magnet. This was not originally existing. So that induced North Pole is getting closer, and that's the interaction of these two opposite poles gives rise to attraction. But if we take this North Pole, the bar magnet totally away from this thing, there would exist no magnetic field lines like this, and this iron nail would altogether lose magnetic property completely. So that's the idea of soft magnetic material and hard magnetic materials. Typically, do you guys understand what is an alloy? Did I ever talk to you about alloy? What do you understand by this word, alloy?
Mixture of metals.
I'll need one more word with that.
So metalloids.
Homogeneous. Let me give you a small comparison so that it makes good sense. I have a reason to tell you this. An alloy of a metal or multiple metals, alloy can have non-metal compounds elements as well. For example, you can have carbon, you can have a little bit of phosphorus or sometimes sulfur, which are not intended, but sometimes we have those elements present. Carbon is always present in an iron alloy. It's very difficult to get rid of iron completely unless we go for electrolysis. If we make iron from iron ore to the blast furnace, which is the typical industrial process, there's always some significant portion of carbon. So I wouldn't say it's only the mixture of multiple metal only. I'm going to say it's a mixture of multiple elements where the significant portion is metal. Let's put it that way. For example, we can make bronze using copper, zinc, and zinc, I believe. Yes. Bronze is made from copper and zinc. So if we merge these two, we get bronze. And pittoler namta ami bhule gechi.
So what does homogeneous mean?
Acha, homogeneous means what? Exactly. Coming to the point. Homogeneous means the percentage composition of all the constituent elements is uniform, no matter how big or small of a piece you take from the sample. I'll give you a small example. Let's say you have a glass of unsaturated saltwater solution. Let's say you have a glass of unsaturated saltwater solution, which means there is no crystal salt. All the sodium chloride is totally dissolved. You cannot see any crystal, but you know that there is salt present in the water. You must agree, because it's a solution, every part of this solution is equally salty. The ratio of water molecule is to sodium chloride in terms of mass, in terms of number of particles, is that ratio is same everywhere. Wouldn't you agree?
Yes, sir.
It's equally salty everywhere. An alloy for a metal is of that property, but in a solid state. We define an alloy then when it is not only a mixture. For example, come to think about it, whenever we mix up cement with sand and water, we get what is called it's called English.
So what?
এই যে মানে সিমেন্ট মিক্সচারটাকে যেন কি বলে? ভুলে গেছি আমি।
Sea water.
No, cement mixture. আচ্ছা, আমি let me give you a different example. মনে করো হচ্ছে আমরা ঝালমুড়ি বানাচ্ছি। We have muri, we have chanachur, and we have other particles as well. So you give a good mix, but you can never make sure that even if we take a small bit of part or a large bit of part, the percentage constituents of all the individual particles will be exactly same. That's what we call a mixture. A mixture will almost always have disproportionate percentage of individual constituent components, whereas an alloy would have the same portion, which means if we have a piece of block that is defined to be an alloy of iron, whether you take a small chunk out of it or if you take a large block out of it, and if you bring apart all the individual parts, you're going to always come up with the same percentage ratio. That's what is meant by alloy. So in other sense, you can say the word homogeneous actually means an uniform mixture, or like a solution kind of mixture, but in solid state, where the percentage compositions are exactly same no matter where you look at. Make sense?
Yes, sir.
Beautiful. So the reason I'm coming to the point of alloy, because I moved away from the point of soft material and hard material. Soft materials are usually the materials of iron or alloys of iron which has a higher percentage of carbon. They tend to behave not to stoichiometric behavior, but they can behave as required for a magnetic field whenever necessary, which means if let's say we have an iron nail over here, if we bring the bar magnet over here in this fashion, this will be the north pole and this will be the south pole. If we reverse it, let's say there is that same iron nail, I'm now drawing by blue, let's say, but if we bring a bar magnet over here with north pole over here and south pole over here, this iron nail is simply going to change this side to, sorry, I miswrote. Let's say if we bring the south pole over here and the north pole over here, this iron nail is simply going to become north pole over here and south pole over here. It's going to immediately change its magnetic polarity and always give us attraction. So soft magnetic material will always become magnetized in a convenient way that is easier for it to cope with the existing dominant magnetic field provided by an actual iron, or maybe in some cases, or I should say in most cases, which is provided from electromagnets. Electromagnets we're gonna talk about in the next class. But that's the idea of a soft magnetic material. Whereas hard magnetic materials are usually iron alloys which has the less percentage of a carbon, most commonly known as steel. So if it ever comes in your exam that name one hard magnetic material, you must say steel, STWL. You don't have to say high carbon or low carbon steel, just say steel. Steel is the acceptable example. Steel materials or hard magnetic materials mean that they're difficult to magnetize. If they are not magnetized, I mean, let's say you made a steel piece out of your foundry right off, it's not essentially magnetized, it's just made. So you do not put into any magnetic property, but it has all the necessary components within itself to show itself as a magnet, but it's not magnetized. It's not magnetized yet. For example, should I give an example? Oh, no, never mind. I was thinking of a pretty good example, but that might undermine some people. Not gonna get that. Anyway, so a steel piece which is not magnetized yet is not going to be, if you try to magnetize it, is going to show some significant reluctance or significant unwillingness to become magnetized. So we're going to have to put in some good effort to make a steel bar or a steel specimen, bar or cylinder, whatever, a steel specimen into a magnet. But once we can magnetize this, it's going to retain the magnet. It's going to work like a permanent magnet for the upcoming future. So that's the important part. Hard magnetic materials are difficult to magnetize, but once magnetized, they're going to store that magnetic property. Soft magnetic materials are easy to demagnetize and easy to magnetize. That's the key difference. How can I do magnetization onto multiple objects? There are three different processes. One is the single stroke method, the other one is the double stroke method, and the third one is the electromagnetic way. I'm not going to talk to you about the electromagnetic way right now, but I'm going to get back to this third process in the electromagnetic, coming back from the electromagnetism chapter, so which is going to be right off in the next class. So I'm just going to show you these two processes and we'll call it a day. Single stroke method and double stroke method. Let me just show you the figures. Beautiful picture. This is also good. Not too shabby. Okay. Can you please read the letters at least? What is this letter?
A.
What is this letter?
Small letter A.
Small letter A. Beautiful. Did you guys know that where does the name of these two different shapes, uppercase and lowercase, comes from?
Greek letters.
I mean, we call this uppercase A and this we call this lowercase a. These are called uppercase, these are called lowercase. Do you guys know where does these names come from?
So I think it comes from Greek.
Sorry?
It comes from Greek.
Greek?
Greek.
No. It's not from Greek. It's from the earliest case of printing technology, when people actually put metallic heads of letters onto a plank and made the whole thing, and they would press it against white paper to make the painting. So let me just show you one image, it will make sense. Small piece of history, but important. I find these things important. interesting, not important. Here is the thing. So all of these boxes have individual letters. This is the boxes. I mean, this is the place where actually people used to pick up the letters, put them along a plank, and they're gonna set it onto a format, which is gonna be bound on all sides, and they're gonna press it against a piece of paper. Before the whole printing technology like inkjet printer or laser printer came about, this was the way books were printed. And this upper box always hold the capital letters, and the lower one always hold the small letters. That's where the name uppercase and lowercase comes from. You understand?
Yes, sir.
Anyway, so I'm going to get through this pretty fast. The process of single stroke method or single touch method works like this. Let's say this NS bar, which is shown as diagonal, is actually permanent magnet, and AB over here is a steel bar that we want to magnetize. So this is the steel bar which we want to magnetize using this magnet. The process is like this. We're gonna touch one end of the North Pole onto side N, and we're gonna pull it like that. Then we're gonna move it all the way back and once again touch the same thing over here. So what they are trying to mean is something like this. Let me just draw this for you so that I can make sense with it. So this is our steel bar, A and B. Let's say this is our bar magnet, north and south. So the single touch method is something like this, or single stroke method. Why? We're going to bring the bar magnet, make it contact over here, rub it in one direction, lift it up, bring it once again back to the same location, rub it in the same direction, lift it up, and like that. That's the single stroke method. We're not going to stroke back and forth. We're always going to stroke with one single pole in one direction. And this will ultimately lead to us to lead AB bar to become north pole on the northern side and south pole on the north end side. So আমরা যে এন্ডটা নিয়ে রাফ করতেছি স্টার্টিং এন্ডে ওই পোলটা ক্রিয়েট হয় এবং অপোজিট এন্ডে অপোজিটটা ক্রিয়েট হয়. So once again, this is a part of the thing that I'm telling you what happens when. I'm not telling you why that happens. I mean, why this end becomes north pole, that is not covered in your syllabus. I also don't know this thing, but if you ask me why does it happen, I cannot answer that. The double stroke method, which can give to the process to the creation of a much stronger magnet, uses two different magnets, and we have to use two opposite poles to rub off from the center on the opposite side. So here this north end is starting from the middle and rubbing towards the end of the B, and this south pole is starting at the middle and rubbing towards the end of north. So we have to do this simultaneously and do equal number of strokes. So take all the way to the end and then lift it up and bring it to the center once again, and then lift it and pull away, and that's the process of double stroke method. In the double stroke method, ideally, if you just consider the single stroke method and double stroke method, I mean, under this north pole we should have had another north pole, and under this south pole we should have had another south pole. But a single piece of object which is not broken cannot have this kind of north south pole over here. Practically what this essentially leads to build up, the last end becomes the opposite pole. So the north pole rubbing side edge at the end becomes south pole, the south pole rubbing side at the end becomes north pole, and the whole thing becomes a north pole south pole bar magnet. And this process produces much stronger magnet compared to this one for the same number of strokes. So if you do 10 strokes over here, if you do 10 strokes over here, this thing is gonna definitely become a more stronger magnet. This whole thing of becoming magnet is done, it can be explained by the idea of dipole. Dipole is not in your syllabus, but I'm going to talk to you about dipole a little bit in your next class, just to give you an idea, some sort of physical, some mechanism to visualize how does the magnetism actually works for microscopic cases. So we'll start from that in the next class, from the dipole, and then we're going to slowly move on to the electromagnetism chapter. ঠিক আছে বলবান?
Yes, sir.
আচ্ছা, আসসালামু আলাইকুম। I have another class. So, assalamu alaikum. Allah Hafiz.